In this video, we're going to be talking about an exercise that is very common on exams, and the reason behind it is that it has a very practical use in the real world. Let's say you got a random cable that you don't know what its characteristic impedance Z0 is and what its attenuation constant alpha is. You measure what the input impedance Zin is when we have an open circuit as a load, or in other words, when our load impedance is very high, because if we just had air in between, we wouldn't have current. And we call this impedance Zin-O, where O stands for open circuit. And then we also measure what the input impedance Zin is when there is a short circuit as a load. And we call this Zin-S, where S stands for short. And then we use this information to find the characteristic impedance and the attenuation constant of the transmission line. In part 1, we're going to find the characteristic impedance Z0, and in part 2, the attenuation constant alpha. Let's take a concrete example. Let's say that our transmission line is 20 meters long, so L is 20 meters, and that the system is in sinusoidal steady state, which means that we can use complex number to simplify our life and to make math easier. We have our input impedance when there's an open circuit that is 50 plus 150J, where J is just the imaginary unit. Some people use I, some people use J, but usually in physics, most people use J. And our other input impedance, Zin-S, is 80 plus 40J ohms. Now we are asked to find Z0 and alpha. Now to start off, we use a very famous formula. That is Zx prime equals Z0, ZL, which is the load impedance, plus Z0, which is the characteristic impedance, hyperbolic tangent from gamma x prime, Z0 plus ZL, hyperbolic tangent, gamma x prime. Now, by x prime, I mean that we start the distance from right towards the left. And when I talk about x, it's when it goes from the source towards the load, or from left to right. This formula is valid for every x prime, so we can substitute. Let's first try for Zin-O. Zin-O is equal to Z0, ZL plus Z0 hyperbolic tangent 20 gamma, Z0 plus ZL hyperbolic tangent of 20 gamma. Now I wrote 20 gamma because the length of the line is 20 meters, and when we say input impedance, we mean at the beginning of the line. And since we had x prime inside the formula, we had to substitute that the line is long 20 meters. Now here notice that for an open circuit, we can just say that the load is infinite ohms. So we can write that this is equal to Z0, and we can take in front of the parenthesis ZL, which will simplify our calculation, and inside what we will have left? We will have left 1 plus this term right here divided by ZL, okay? And in the denominator, we will also take the biggest term in front of the parenthesis, and we will have left Z0 divided by ZL plus hyperbolic tangent of 20 gamma. And as you can see, this simplifies to 0. This is also 0, since we divided something by infinity, which is 0. These two cancel, and we have as a final thing, Zin-O is equal to Z0 divided by hyperbolic tangent of 20 gamma. Now we can do the same thing with Zin-S when there's a short circuit. Now I just wrote the formula, and instead of Zx prime, I substitute Zn-S. It's the same exact procedure, and here ZL is 0 because it's a short circuit, and a short circuit is basically a wire with no resistance. So we can just substitute ZL equals 0, and that is Z0 times Z0 hyperbolic tangent of 20 gamma divided by Z0. These two cancel out, and then as a final result we have Zn-S equals Z0 hyperbolic tangent of 20 gamma. Okay, so now that we have a system of two equations, we can just multiply them and we will get, let me just take the formula from above, copied below. So we have a system of these two equations. When we multiply them, we will get Zin-S, Zin-O equals this first expression right here multiplied by the second expression right here. And as you can notice, here we have hyperbolic tangent in the numerator, here in the denominator, so they cancel out. And we get that z in O equals ZO squared. So we have as a final result that this right here is just the square root of both of the input impedances when it's an open circuit and a short circuit. Okay, so we've successfully managed to find the characteristic impedance Z0 of the transmission line. And in part 2, we will find the attenuation constant alpha. That's it for today. Hope you liked this video and ask any doubts if you have them in the comments, and see you in the next one.